Alrighty, let us get started. So today we will start into the first topic of physics for the semester. Now that we've kind of had our math review, I think we're kind of prepared to take on whatever challenges that may bring. The first topic we'll talk about is electricity and magnetism. Now, this is interesting because it's two topics, electricity being one, magnetism being the other, but also a single topic because as you learn, as you get into higher and higher levels of physics, electricity and magnetism are really one phenomenon in this universe. Magnetism arises from electricity, and electricity arises from magnetism. So it's a strange concept, being that they're seemingly two different things. You know, positive charges, negative charges, the electric force, electric fields, circuitry, things like this, being electricity. And in magnetism, you know, magnets, North Pole, South Pole of a magnet, and the force of attraction due to the magnetic properties, things like this. Yet somehow, deep down, fundamentally, they're related. And as you progress, you find out how they're related, how one can give rise to the other, and things like that. For now, we'll keep them separate just to make our life a little easier. And we'll discuss electricity first. And so when talking about electricity, we have a few concepts we need to understand. We need to know about what are the variables, what are the equations, things like this. So the first thing is the concept of electric charge. Electric charge is something in physics. It's part of a group of things, really, one can think about, that I like to call sources. Okay, so there's special characteristics as you move along in physics, which would be referred to as a source of something. And so, for instance, one we already know about is mass. Mass is a characteristic of different objects. The more massive you are, the harder it is for you to move. The greater the gravitational force of attraction, all sorts of things. Well, another way of thinking about mass is that it is the source of the gravitational field. So if you have no mass, then you have no gravity. And so it's the mass of an object that gives rise to a gravitational effect. You have two masses, let's say a planet and a moon, or the sun and a planet. Those two masses, those two sources of gravitational fields, attract each other gravitationally. Or you standing on the earth, you have a mass, the earth has a mass. If you jump, you're going to fall back down to the earth because the earth attracts you by a force. And so that's a property of sources. A source of a certain field, in this case, let's say the mass being the source of the gravitational field, allows for a force between those sources. Okay. Well, electricity, there's a different source. Actually, there's two. Those two sources are called charges. And there are two of them, which means we have a positive charge and a negative charge. Okay. So what is a charge? It's a characteristic of a certain material. Just like mass. I mean, you could try to get philosophical about the question and say, what exactly is mass? We know the effects of mass, we can measure the mass, but to try to describe what is that physical characteristic called mass it's a really difficult question to wrap your brain around. And the same holds true for electric charge. What is an electric charge? Well, it's a fundamental property of whatever material you're talking about. It just so happens that there happens to be two different sources, two different types of charges. With mass, there's only one mass. There's not like a positive mass and a negative mass, or a north mass and a south mass. But with electricity, there's two charges, a positive charge and a negative charge. And some of the characteristics we know about it, for instance, like charges repel, unlike charges attract. So again, just like with the case for mass being a source of the gravitational field, two like charges for mass attract each other. Again, a planet and a moon, they're both like charges, quote unquote, because there's only one kind of charge. It's called mass, a certain source. So two masses attract each other. With electricity, the fact that there's two different types of charge, a positive one and a negative one, it's a little bit more complicated. It's not always going to be attractive. Sometimes it's attractive, sometimes it's repulsive. But what is true is that if you have two sources, two charges, there will be a force between them. What kind of force? Will they be wanting to move towards each other or away from each other? It depends what particular charges you have. And in this case, like charges repel. So if you have two protons, two positive charges, they're going to repel each other. They're going to push each other away. Whereas if you have a positive and a negative, so a proton and an electron, let's say, then they will attract each other. Now, with that, what is the variable which represents this thing called charge? So the source of mass has the variable m, and the unit is kilograms. The variable for charge is q. That's the variable. And its unit is capital C, which stands for Coulomb. Okay. It's a fundamental, well, you can think of it as a fundamental unit. It's not made up of kilograms and seconds and meters, like for instance, newtons is made up. But just like kilograms is a fundamental unit, you can't break it down. Coulomb, the unit of charge, can be thought of the same way. And again, Q is the charge. However, you could have a positive version and a negative version. And the examples we usually think of are things like a proton or an electron or things like that. All right, so now that we know this, what is going to be the big equation we're going to be using here? What kind of problems are we going to want to try to solve or work on, at least for this semester? And for us, what we'd like to do is discuss the force between charges. Sometimes it's called the Coulomb Force. So if you have two charges in proximity to each other, the force between the charges, or at least the force felt by one charge due to the other charge, is given by the equation F equals some number K times Q1, which is how big of a charge is one of the charges, times Q2, how big is the other charge, divided by r squared, where r, of course, is the distance between the charges. Now, K, I said this is just a number, this is a constant. And what you find in physics sometimes is when you have an equation, of course, we're working with certain units, kilograms for mass, meters for distance, seconds for time, things like that. Well, humans created these units, right? A meter is a certain length, but that length, that meter, is not fundamental to the universe. That's just something that was desirable for a human being. Or the time of seconds. Why is a second the important unit? I mean, to the universe, seconds is an arbitrary time length. And so what winds up happening is you create an equation that you use your, artificial human units. And because those units are artificial, they're not fundamental to the universe, the numbers aren't perfect. And so you have to fudge the answer by multiplying by something, plugging a number in there to adjust the answer to give you the right number. Okay, so for instance, if we didn't have this K, whatever the number is, and I'll tell you what the number is, if we just multiplied the charges together, divide by the distance squared, we'd have some number, but it wouldn't match what the experiments tell us the number should be. However, if we multiply that by this number K, of course, people figured out what K is because of the experiments, then we match experiments. And so it's a fudge factor. It's purely, you can think of it almost like a conversion. We get a number that's fundamental to the universe. We convert that number to the units of humanity so that it's useful for us to use. And we do it by multiplying by whatever this arbitrary number happens to be. And you see it in a whole bunch of different equations, not just here. Well, what is this number? It is 8.99 times 10 to the negative 9. Or sometimes, of course, it's just faster to say 9 times 10 to the negative 9. Right? You just round it up a little bit. Now, where does it come from? It's not important to know this now, but when you get into electricity and magnetism as a theoretical subject down the line, you find out that K actually equals something called 1 divided by 4 times pi times some other number called epsilon naught. And this is the number that deals with where are you making these calculations? So, or the experiment. You're putting the charges close to each other, and you're going to measure how hard of a force do they feel against each other. Well, if you put these charges in air, you'll get one type of force. If you put the charges in glass, then the force will be different. If you put it in metal, the force will be different. If you put it in water, the force will be different. So what material this force is trying to penetrate through will change how big of a force the charges will feel. What is their environment? Is the environment conducive to electricity? Does electricity flow more easily through this environment? Or are you in more of an insulator where it's really difficult for electricity to flow? If it's difficult, then it's hard for this force to be felt by the other charge. But if the environment's really easily conductive, if you could easily send electricity through, then the force will be felt much, much larger. And so this epsilon naught is kind of like a measure of how easy electricity can flow through the material. And it's particularly how easy does it flow in a vacuum. So this is some other constant, and it basically tells you how easily does the electric field specifically go through a vacuum. So if you know that number, you do 1 divided by 4 pi times that number, you get this number 9 times 10 to the 9, or 9 times 10 to the negative 9, I'm sorry. So this is what you see when you get to senior level physics, because then you can start modifying, say you're not in air, but instead you're in glass, then you're going to change this number to something else. But for us, obviously, we're just starting out. We're trying to get our bearings, the pure theory. So we're going to use the basic number and just say 9 times 10 to the 9 is this constant. All right, what does a problem look like? A nice basic problem is something like this. You have 2 charges. Let's say you put 1 charge at the origin. Let's call that Q1. And let's say Q1 is 2 times 10 to the minus 6 coulombs. And then you have another charge, and I placed it over here. Q2, let's say, is 3 times 10 to the minus 6 coulombs. And let's say the distance between these 2 charges is 4 meters. The question will be, calculate the force felt by Q2 due to Q1. Okay, so 2 electric charges placed next to each other some distance away. You know how big the 2 charges are. And you want to know, obviously, there will be a force felt by these charges. You want to know, what does Q2 feel because of Q1 being there? If Q1 wasn't there, Q2 would just sit there. However, as soon as I put Q1 down, now there's 2 electric charges, there's going to be a force. What will this force be? This is a nice basic Coulomb force problem. How would we solve a problem like this? Well, you would say, okay, the force, and this is how I would write it. The force on 2 due to 1. Okay, so different professors will have a different way of annotating or labeling what they're trying to solve. Some people do it the other way, backwards of what I'm doing. You could do it whichever way you like, whatever makes sense in your mind. But for me, because what I'm being asked is, what is the force on Q2 because of Q1? Then I say the force I want is the force that's on 2 because of charge 1. How do I calculate it? I just use the equation I saw. K, Q1, Q2 over R squared. Very easy. Plug my numbers in. K, that's 9 times 10 to the minus 9. Q1, that is 2 times 10 to the minus 6. Q2, that's 3 times 10 to the minus 6. Divided by the distance between Q1 and Q2, which I'm told is 4 meters. And you square that. At this point, all you have to do is plug this stuff in your calculator. So I'd get my calculator. I'd say 9 times 10 to the minus 9 times 2 times 10 to the minus 6 times 3 times 10 to the minus 6 divided by 16. And I get the total charge is 3.38 times 10 to the minus 21 newtons. Now, before I box my answer, I have one more step to do. And this step is to figure out, is the force going to push my charge to the right? Or is it going to push my charge to the left? Because the force felt by an electric charge is either repulsive or attractive. How do I know which? The rule was stated above. If you have like charges, they repel. And if you have unlike charges, they attract. So we look at my example. The two charges were both positive charges. So they're like charges. They're both positive, which means they repel each other. What does it mean for the charges to repel? Well, that means Q2 will be pushed away from Q1, which means he's moving to the right. But if I look at Q1, Q1 is pushed away from Q2, Q1 would be pushed to the left. Okay. And now I say, okay, for my problem, I'm asked what's happening to Q2? What does he feel? Well, Q2 feels a charge of 3.38 times 10 to the minus 21. But in which direction? He's being pushed to the right. To the right is positive. So he's a positive 3.38. And now I can box my answer. Now, before I say anything more about this, are there any questions about how to solve this particular example?
Okay, so regardless of which column you're solving for, 1 or 2, the force will still be the same, right?
Yeah, that's an interesting artifact, isn't it? Yeah. I happen to look at what force 2 felt, what Q2 felt. However, if I wanted to see what does 1 feel, well, let's do it really quick. It's really easy. F on 1 due to 2 is exactly the same, Q1, Q2 over R squared. All the numbers are identical, so I get the same number at the end. The difference, however, is the direction. Q1 feels a force pushing him away from Q2, which pushes him to the left. So he will have a negative sign on it because he's moving to the left. Okay. And that's the big key. And that's the thing I said I wasn't going to say yet, but this is a perfect opportunity. This is one of the big sticking points I have seen all the years I've been teaching physics. In electricity and magnetism, one of the places mistakes get made is with whether the force is going to be a positive force or a negative force. Because what's tempting to do is to plug the numbers into your equation. Remember, Q could be positive or it could be negative. You plug them in as they are, and you get an answer. And you say, whatever that answer is, that's the answer. But that's wrong. Instead, what you're going to see in some textbooks is the equation goes like this. F on 1 due to 2 is some number K times absolute value of Q1 times the absolute value of Q2 over R squared. Okay. Now, I don't write it like that just because it's a little bit more difficult to write, having to put the stupid absolute value signs. So what I do as a teacher is I just give you the basic equation. And then after I tell you the equation, I give you this warning. And the warning goes like this. Every time you go to make a calculation using this equation, no matter what the charges are, whether they're positive or negative, doesn't matter, always plug them in as positive numbers. However, the answer you get, you will have to make positive or negative based on whether you know, will the force be pushing the thing to the right or to the left? Or if we're looking up and down, is it going to be pushing it upwards or downwards? Okay, because unfortunately, the equation does not tell you the direction. As you can see with this particular example, The first one I did was perfectly fine. The charges were positive. The constant K is positive. The distance between them is positive. So all the numbers are positive. The force I get is positive, and it matches. But in the second one, where I'm looking at what's happening to Q1, same is true. Everything's a positive number there. However, I know that since these two charges are both positive charges, they're like charges, they will repel each other. And since Q2 happens to be on the right side of Q1, that means Q1 is going to be pushed to the left. So the force that Q1 feels is a negative force because it's pushing him to the left. But that negative does not pop out of my math. There's no negative anywhere in my equation. So unfortunately, you have to put the negative sign or the positive sign yourself. The math will not tell you. And it gets really confusing when some of the charges are negative charges. Because then you could get a negative answer, but maybe the answer should actually be positive. Because even though you get a negative answer from the math, the force is actually pushing the thing to the right. So to avoid all the confusion and everything about it, every single time you go to calculate a force on a charge due to another charge, no matter whether those charges are positive or negative, place the numbers in your equation as positive charges. So every single time you get an answer, you'll get a positive answer then, of course. But then you take the extra step to look at your situation. You say, the charge I'm looking at, which way will he be pushed? Is he going to be attracted to the other charge, or is he going to be repelled from the charge? And that'll tell you, is he moving to the left or to the right, depending on where the charges are. Okay, so that's a very, very critical piece. Of course, the numbers will come out the same, but whether it's a positive charge, positive force or negative force is a very important thing to know. And the only way to get it is to do it yourself. The math will never, ever be able to give you the number. The negative or the positive, I should say. Okay, so does that make sense about the positive and negative part of the answer?
Yes.
Yes.
Okay, good, because it's especially, we're doing tests. We have a 50-minute or an hour and 15-minute test, and we're rushing through trying to finish the whole thing. It's very easy to calculate out your answer, especially with a bunch of numbers in your equation. And then you just forget to test whether it should be positive or negative. You just box whatever you get. And it doesn't take off all the points, but it takes off some points. And it's better to take the extra 5 seconds to look at your picture and say, will Q2 move to the left or to the right? In this case, he's moving to the right, so he's positive. Q1, if Q1 was the thing I'm solving for, he moves to the left, so I have to make my answer negative. And then you don't lose points because of the directionality. So that's why textbooks have the absolute values on the Q's. They're telling you, always make them positive. And then on top of that, the answer you get may have to be changed from positive to negative, depending on the particular problem. But this is all there is to it. Basically, given two charges, some distance away from each other, some can be positive, some can be negative, whatever. How do you calculate how much force one of the charges will feel due to the other? Plug it into this equation. Let's do another example. Here's our charges. We'll place one charge. Q1 is 3 times 10 to the minus 3. Or not 3, I'm sorry. 3 times 10 to the minus 6. Sorry. And then we'll have Q2 will be negative 1 times 10 to the minus 6. And I'm told that Q2 is placed 2 meters above Q1. The question is, what is the force felt by Q2? So again, we're going to go about this the same way. I only have one equation so far. That equation says that the force on 2 to 1 is some number k times Q1 times Q2 over r squared. K, that's easy, 9 times 10 to the negative 9. Q1, 3 times 10 to the minus 6. Q2, negative 1 times 10 to the minus 6, but I'm going to put it in as a positive number. 1 times 10 to the minus 6. Divided by the distance from 1 to 2, happens to be 2 meters here, so 2 meters squared. And now I have my equation. Plug all these numbers into my calculator. I have 9 times 10 to the minus 9 times 3 times 10 to the minus 6 times 1 times 10 to the minus 6, all divided by 4. And I get 6.75 times 10 to the minus 21 newtons. And then last step, is this going to be a positive force or a negative force? Well, Q2 is negative, Q1 is positive. They're unlike charges, so they're going to attract. That means Q2 wants to move towards Q1. And towards Q1 means Q2 will be moving downwards. And I know the standard is downwards is a negative direction, so the force is negative. Okay, if I were solving this for Q1, it'd be exactly the same answer, except Q1 is attracted upwards towards Q2, so his force would be a positive force. All right, so any questions about this particular example? Now, the last example I'd like to show is where the complication really comes in. This is where vectors start to become important. Let's say I have a charge Q1, which I'll call 1 times 10 to the minus 6. Then I have Q2 sitting over here. I'll let him be negative 2 times 10 to the minus 6. And then I'll have a Q3 up here. And I'll call it 3 times 10 to the minus 6. By the way, these unit 3 times 10 to the minus 6, that's because the general size of a charge in the real world is what's called a microcoulomb. And so just like there's millimeters and centimeters and kilometers, well, there's a coulomb, but then there's centicoulombs and kilocoulombs. Well, one of them is microcoulomb. And the micro, if you remember from units, micro means 10 to the minus 6. Okay, so if I said Q1 is 1 microcoulomb, what it means is 1 times 10 to the minus 6 coulombs. Okay, so sometimes if the professor who's making the question just wants to write it quickly, instead of writing out 2 times 10 to the minus 6, they'll say 2 microcoulombs. So just know that's what it means. Microcoulomb means 10 to the minus 6 coulombs. All right, well, here's my example. Obviously, this is more complicated because now I have 3 different charges. And maybe the question I'm asking is, what is the force felt on Q1 due to the other 2 charges? Uh-huh. So obviously more complicated. Now, instead of there just being two charges, and so if you want to know how much force is felt by one of the charges, well, there's only one force there. It's the force due to the other charge. Here, if I want to know what's the force felt on Q1, there's two separate charges trying to move him. Q2 is trying to attract him to the right, so I could show that. Q2 wants to attract him because they're unlike charges, but also Q3 is like charges, they're both positive, so Q3 is trying to push him downwards. So he's feeling two different forces right now at the same time. A little bit trying to move him to the right and a little bit trying to move him downwards. So we want to know what's the total force felt by Q1. Well, that's a lot like what we saw with first semester physics. You have, you move a certain amount in this direction, and then you move a certain amount in that direction. Where did you end up? Well, there's a vector pointing in one direction, a vector pointing in the other direction. To get the final, the total, you add those two vectors together. Same is true here. There's a force on 1 due to 2, and there's a force on 1 due to 3. Each force is a vector. If you want to know what's the total force, that means add these two force vectors together to get a total force. The issue comes in with the fact that one of the forces is to the right, the other force is downwards. That's different directions. And what we saw with vectors is you don't have the ability to add vectors if they point in different directions, unless we use our little trick with the components. We take each force, we break it up into X and Y components. Then we can add the X's together with the X's and the Y's together with the Y's. And we'll have a final force, X component, and a final force, Y component. With those two, you can get the magnitude and direction of the final force, which is what you want. So that's going to be the big prize here. That's going to be what is the most complicated part of what we're going to learn with electric force. Given a set of charges, all competing with each other, all putting forces on each other, you want to know what's the total force felt by one of the charges. The way we're going to do it is we're going to say the force felt on 1 is the force felt on 1 due to 2 plus the force felt on 1 due to 3. Right? If these are vectors, which of course force is a vector, then if I want the total force on 1, what I need is what's the force on 1 because of this charge, and then what's the force on 1 due to that charge. I add up all those separate forces together. There's vectors, so I have to add them as vectors, and I get some final magnitude and direction of the force on 1. And that's going to be the job. How do we go about doing this? Well, let's look at F12 first. The force on 1 due to 2 will have an X component, and a force on 1 due to 2 will have a Y component. So let's just look at that one. Forget about charge 3 for now. We say, okay, what is the charge on 1 due to 2? Just generally speaking. Well, of course, it's K, Q1, Q2 over R squared. So it's 9 times 10 to the minus 9. So you know what? I think, I'm sorry. This whole time, whoops. This whole time, what the heck is going on? Thank you. I've been saying 9 times 10 to the negative 9. I'm sorry. It's actually 9 times 10 to the 9, not negative 9. What am I doing? 9 times 10 to the 9. I'm thinking of the magnetic one. The magnetic one is 4 pi times 10 to the minus 7. That's where the negative is. So these numbers, let's see, I said minus 9 and it's plus 9, so it's 18. So this is probably negative 3. Yeah. I think that's right. I think this is times 10 to the negative 3. It's just going to change the exponent there. It won't change the actual numbers. So definitely 9 times 10 to the 9. Easy to remember. K is 9 times 10 to the 9. All right. So anyway, back to it. 9 times 10 to the 9 times Q1. Q1 is 1 times 10 to the minus 6. Times Q2 is negative, but remember, I always plug my charges in as positive numbers. 2 times 10 to the minus 6 divided by the distance between them. Oh, I didn't give you the distances. So let's say the distance here is 3 meters and 4 meters. Okay. So the distance from 1 to 2 is 3 meters squared. And then I say, all right, the same would hold true for the y component, right? It's the same equation. The difference here is look at these two charges. Q1 and Q2 are in line horizontally. So I know Q2 is going to feel or is going to force Q1 horizontally. There's an X force, but he's not going to push him up and down, right? He's going to attract him to the right, purely to the right. So that tells me the y component is going to be 0. Charge 2 will not push charge 1 up or down. He'll only pull him left or right. So the y component is easy. That's just 0. The x component, that's what I calculate here. But then we can do the same for force 1 due to 3. There's going to be an x piece and there's going to be a y piece. And we look at it. For charge 1 is at the origin, charge 3 is above him. I know the force on 1 due to 3 is going to be either up or down, either attractive or repulsive, but it's up and down. And it's not going to be at all in the x direction. So that tells me the x component of this force is going to be 0. There is no x component of this force. It's purely a y force. And what is that y force? Again, K, Q1, Q3 over R squared, which is 9 times 10 to the 9 times 1 times 10 to the minus 6 times 3 times 10 to the minus 6. I believe I made it. Yep. Divided by the distance between them, which is 4 squared. Let me look at the positives and negatives here. Q1 will be attracted towards Q2 because they're unlike charges, which means the force on 1 due to 2 is a positive force in the x direction. So he's going to be a positive answer. For 3, Q1 and Q3 are both positive charges, so they repel each other, which means Q1 is being pushed downwards. So the y piece is going to be downwards, which is negative. So he's going to have a negative answer. Now, whatever the answer is, don't worry about what these numbers are. We're going to put it in my calculator. We get an answer from all of this. At this point, what do? We've set up everything we need. Each charge gives us a force. Each force is going to have an x component and a y component. We calculate all those things out. Here they all are. Then we say, okay, the final force on 1 in the x direction is going to be the force on 1 due to 2 x component plus the force on 1 due to 3 x component. And so I just get my numbers from what I just calculated with this stuff here, plug them in, and I'll have an answer for that. Same holds true for the total force on 1 in the y direction. Well, it's going to be the force on 1 due to 2 y component plus the force on 1 due to 3 y component. I calculated them out here. Here's the y component piece. Here's the y component piece there. I add them together. I get a certain number for that guy. Okay? Whatever they happen to be. It doesn't matter what the answers are right now. We're just looking at the technique. Now that I have these two pieces of information, I know the total force x component and the total force y component. Well, if you remember from vectors, if I want the magnitude and the direction, the magnitude of the total force on 1 is a square root of the force on 1 x piece squared plus the force on 1 y piece squared. So I'd plug those numbers into this little equation here, and I'd have a total force on 1 magnitude. That's half the answer. The other half we need is, of course, is the direction. And we remember direction was inverse tangent of the y piece, F1 y piece, over the x piece. And that'll give me an answer for the direction, some angle. And then remember, for the angle might be wrong sometimes, so maybe have to add 180 to make it right, depending. Or maybe not. Whatever it is, you'd have your two answers, and those would be your two answers: the magnitude and the direction of the total force felt by charge 1. So that's what we're going to do. That's going to be the most complicated question we have for this particular topic. We'll have an arrangement of charges. Each charge, we know what the charge is, we know the distance between them, all of that stuff. And we're asked for the total force felt by one of these charges. How do we do it? Well, we just say, well, the total force felt on this charge is the sum of each individual force. So charge 1 will feel the force from charge 2, and then charge 1 will feel the force from charge 3, and so on. And if you add up each of those forces, you get the total force. But because these are vectors, those forces may point in different directions. And so what we have to do is take each one of these individual forces and get an x and y component for each. At this point, this is where the equations come in. The k, q1, q2 over r squared business. You look at your problem and you say, okay, for this particular force, let's say F1 due to 2, I need an x piece and a y piece. Will this force have an x component? Well, if the force points in the x direction, then of course it does. So I do the equation. Will it have a y component? Well, in this case, because 1 and 2 are both horizontal there, then there's going to be no y component. There's no amount of force due to charge 2 that's going to move charge 1 up or down. So you know automatically his y component is just 0. Then you're done with that particular force. You move on to the next one, F1, 3. Same thing. Will he have an x component? Oops. Well, no, because 1 and 3 are vertical with each other. So they're going to be purely in the y direction. So that means the x component is going to be 0. However, the y component, I calculate using my equation. And then I make sure I have my positives and my negatives correct. Is the force that I'm talking about in the x direction to the left or to the right? Or in the y direction? Is it upwards or is it downwards? That tells me positives and negatives. Once I've done all those calculations, I'm now set to get my final stuff. I add up all the x component stuff together to get a final x. I add up all the y components together to get a final y. With those final x and final y, that's when I do my magnitude and direction calculation. Okay, so it's serious business. You know, this topic is one of the more complex topics you get, and it's a place where lots of mistakes can be made. Just because usually at this point, we're not all that comfortable with vectors yet. And using vectors and equations all at the same time. But you can see each step itself makes sense. So if, as long as you go step by step, stay as organized and as neat as you can, just take your time through it, you'll avoid most of the silly mistakes like positive and negative problems. And just think of it as if it's a vector problem. You have two vectors, they point in different directions, and you need to add those two vectors together. Break the vectors up in x and y components, add the x's, add the y's, magnitude and direction. It's purely a vector problem. The only difference is in the components section, we're using a physics equation to calculate the numbers. That's what's unique here. All right, so that's the theory. Are there any questions about how to do this type of problem? Now, the problem can get worse from a mathematical standpoint if instead I had asked, what's the total force felt by charge 2? I chose charge 1 for this problem to make it the easier version. If I were looking at what happens to charge 2, now all of a sudden, one of the forces is going to be an angled force. Okay. And so now I'm going to have cosines and sines to worry about for my x and y components. What I'm going to do, since this is an intro course, is I'm going to skip those. When I give a problem that's going to be like this, I will try to make the problem where the forces will either be pure x forces or pure y forces, just so that we learn the theory without having to muddy it up with the really hard math. When you get to general physics 2 or general physics 3, that's where you'll get these types of problems where now the angles are involved. And so now you got to worry about sines and cosines and stuff. But for our class being the intro, just kind of getting the overview of stuff, we'll avoid that. And you'll have problems more like this, where one of the components is 0, the other component is whatever you calculate it to be. So that's the good news I have for you, I guess. But other than that, I'll go ahead and leave it like this for today. But what I will suggest is I'll give you another example and take the weekend to work on it. See if you can get it yourself, and then next class we'll do it together and match. But take the example similar, where we have multiple charges like this. Q1 is 1 microcoulomb. Q2 is 3 microcoulombs. And Q3 is -4 microcoulombs. Okay. Given the distances from 1 to 2 is 2 meters, and 2 to 3 is 5 meters. The question is, calculate the total force felt by Q2. Okay. So very similar, almost identical to this example, except the arrangement of the charges is slightly different. But you're going to go through the same method. So this isn't homework in the sense of you'll have to turn this in. This is homework in the sense of practice this, try it yourself. That way, next class, if you got stuck somewhere, you'll have a particular question to ask, or you'll know kind of how you're doing, because the same is true for me as for everybody. When you're watching a teacher work a problem, it makes a lot more sense to follow the steps than if you're doing it by yourself and you don't have someone talking you through it. Okay, so you have to try it yourself without someone else doing it in front of you to gauge how well you understand it. If you can't do it, that's okay. We just started. This is the first day doing it. If you can, great, then you're ahead of the game. But definitely try it. See how far you can get. See if you get a final answer. And like I said, on Tuesday, we will check. I'll do it myself in class, and we'll check our answers. But this is the first topic, Coulomb force. Given a set of charges, what's the force felt on one of the charges due to the others? Okay, so unless you have any questions, you're free to go. I will see you on Tuesday.
Thank you.
All right, no problem. See you later.